1, 2, prova. Ok. Ok. Okay, please. Everybody, please take a seat. We're going to start again. Guys, please take your seat. Let's start again. Thank you very much. Come inside. Thank you. Thank you very much. So we are starting this section called Breaking the Chain. And we are going to listen to a speech enhancing Bitcoin security and performance with a strong consistency via collective signing. Speaking will be Eleftherios Kokorias. That's right? Okay. Thank you.
So yeah, this is joint work with Philip, Nicolas, Ismail, Linus, and Brian from EPFL. So we are trying to scale Bitcoin, and what we have now is not real-time verification. We pretty much need to wait about 1 hour to be sure that the transaction is going to stay in the blockchain, and also very low throughput, around 4 transactions per second. And as Arthur showed, we might get it to 60, but that's it. So we decided to do something a bit more radical. And what we managed to get is irrevocable transaction commitment in about 20 to 90 seconds with a throughput of close to 1,000 transactions per second, where we are more robust against double spending attacks, eclipsing attacks, and selfish mining. And we can also have lightweight clients that verify that their transactions inside the blockchain without the need to trust a full node to get that information. And how we do that? We change the consensus algorithm of Bitcoin from the probabilistic Nakamoto to practical Byzantine fault tolerance. We use collective signing to actually scale PBFT to thousands of nodes instead of the 4 that is usually deployed to. We use proof of work in order to have an open permissionless ledger and not the closed one that PBFT has. And we use the ideas of Bitcoin and G to also increase the throughput a lot more than what Bitcoin currently has. So as an outline, we're going to look a bit into Bitcoin and identify what is the problem we're trying to solve. And then we're going to change the consensus into PBFT. We start with a very strawman where we just have a number of servers that run PBFT in order to append the block. We're going to see the problems there, and we're going to solve them step by step by opening the consensus group to have mining, removing MAC-based authentication and adding collective signing for higher scalability, decoupling transaction verification from leader election to get higher throughput, and we're going to evaluate it and then discuss about future work and conclusions. So this is the blockchain. We know it. And as also Arthur showed, we can have forks, and this is bad because a client doesn't know if his transaction is going to persist. Forks are resolved by just having one more block being mined on top, and the honest majority is going to switch to the longest chain. So for a naive client that sees his transaction inside the blockchain, he's going to say, OK, I'm safe, it is in there. But again, as Arthur showed, we can have late forks, and this is going to just remove the 2 last blue blocks. This means that clients that thought that their transaction actually is in the blockchain now isn't. And this is how we can double spend, for example. And the problem there is that although we see the transaction inside the block, there is no verifiable commitment of the system that this block is going to persist. Clients have to rely on probabilities to gain enough confidence that their transaction is going to persist, because the deepest the block that verifies transactions inside the chain, the harder it gets for the attacker to create this fork attack I just showed. So we're going to change that, and we're going to start by just implementing PBFT on 3F+1 trusted servers that can withstand the failures just like the theory says. And this is already better because we get non-probabilistic strong consistency. Once a block is appended inside the blockchain, then there is a commitment by the supermajority of the servers that this is going to be there forever. So instead of 6 confirmations, we just now wait for 1. Also, we cannot have late forks and inconsistencies because the majority is not going to allow for any fork to happen. They're not going to commit to a forking block because they are honest. So this is good, but it's utopian. We cannot just implement it on top of Bitcoin and be happy and have party. And they have many problems. First one is that PBFT needs a static consensus group that is already decided before the protocol starts. Second and most important is scalability in multiple domains. First of all, the communication pattern that PBFT uses, it's very dense, and this limits the consensus group size. And as we know, PBFT is usually deployed into 4 replicas or at most 15, but we want hundreds of miners to participate. Secondly, it has high client-side verification cost because every client will need to verify each individual commitment of every node participating in the consensus, which would be pretty hard for mobile devices to verify every time 1,000 signatures. And also, because it uses MAC-based authentication, this means that there is no third-party verifiability, which means that every client has to have a predefined share secret with every participating service in the consensus. And if we say we have 100,000 clients and 1,000 servers, this scales really badly. We cannot really have so many shared secrets. So we're going to solve the first problem. We're going to open the consensus group, and we're going to do that without suffering from a Sybil attack by reusing what Bitcoin uses, which is proof of work. We have miners that mine blocks, and every time they mine the block, they get 1 consensus group share. Not every miner has the same voting power in order to preserve the balance of power of Bitcoin. So the miners have a percentage of shares proportional to their hash power because every time they mine 1 block, they get 1 share. So if they mine 10 blocks, they're going to get 10 shares, and this gets proportional to how many blocks they mine. Finally, we're using a window mechanism in order to allow for inactive miners and dynamic membership. So there's a window that shifts every time a new miner finds 1 block so that we only look into the miners of the last 100 or 1,000 blocks in order to define our consensus group. Second problem we are going to solve is moving from MAC-based authentication to collective signing. And of course, the first logical step before collective signing is just using digital signatures. And we can do that more efficiently than what they used to do when PBFT was introduced 15 years ago because we can use elliptic key cryptography, which is a lot more performant than standard public key crypto. And what we get out of that is third-party verifiability. This means that now the clients do not need to have predefined share secret with the servers. They can just get the block, look at the signatures, and verify them against the public keys of the miners. So in order to find these public keys, we need some kind of PKI. And we construct the PKI out of the proof of work that the blockchain already has. Every miner adds his public key inside the block that he mines, and because of the proof of work inside that block, we can be sure that the key inside the block is trustworthy enough to represent the vote of the miner that actually created that block. Finally, this third-party verifiability enables us to have sparse communication patterns like ring and star topologies in order to have higher scalability. However, we wanted to do better than what seemed to be the easy approach, and for this reason, we had to answer 2 questions. The first is if we can have better communication patterns than ring or star topologies, because the ring topology has n sequential steps, and the star topology needs a leader that has to have all the load on him. And if we look into multicast protocols that can transmit information in sublinear steps and they distribute this propagation of the block, we can see that they just use trees. So this is what we're going to also use. The second question is if we can allow lightweight verification without having to verify n consecutive signatures every time we get a block. And as is already introduced, we are using Schnorr multi-signatures that can be verified in constant time, no matter how many signers are multi-signing the block, because they aggregate them. We didn't have to create a new protocol. We're just using the collective signing protocol that was introduced 6 months ago in IEEE SMP conference. I'm not going to say exactly how collective signing works, you can look into the paper. Some intuition was already introduced by using Schnorr signatures in the previous talks. But what we can get out of there is an efficient collective signature that is verifiable as a simple signature. This means that for the 825.519 curve, instead of having 9 kilobytes of signatures being transmitted for 144 signatures, we just transmit 82 bytes and verify them with one cryptographic computation. And as you can see, for 1,000, it just doubles in byte instead of getting 7 times more as without Schnorr multi-signatures. So we are using collective signing. This is good. We can scale our system, but collective signing is not Byzantine fault tolerant. A leader can withhold the blocks in order to attack the system. However, we used collective signing as a primitive in order to implement the Byzantine fault tolerant protocol by having 2 consecutive rounds of collective signing to be interleaved for 1 PBFT round. The first collective signing rounds implements the prepare phase of PBFT, and the second one implements the commit phase of PBFT. You can see more in our paper that we presented 2 months ago in using security. And this is good because now we can have Byzantine fault tolerance in Bitcoin in a scalable way, and there is now a verifiable commitment of the system that the block is going to persist, which means that the client is going to get this collective signature, verify it, and be happy, ensure that the supermajority of the mining power believe that this block is correct, and they're mining on top of it, and he's good to go. The second problem is throughput, and as Arthur again showed, it is limited by forks. We cannot get huge blocks. We cannot get very high frequency because both stuff will actually decrease security. And in our case, we are also going to lose liveness. So what we are doing is we reuse the ideas that Gunsirer has presented, like in the first scaling Bitcoin, I think, about Bitcoin and G, which makes this key observation that mining blocks actually implements 2 different functionalities. The first functionality is verifying transactions because every block has transactions inside that are verified. But the second is that it also elects a leader. So once a miner mines a blocks, he gets the right to verify transactions. He doesn't use it much in Bitcoin, but as they showed in Bitcoin and G, it can be really handy. We enhance Bitcoin and G with our BFT protocol in order to increase its security so that we can't have double spending, we can have one confirmation to be all we need, and also we can prevent the leader from misbehaving and then searching for poison transactions and stuff. So we reuse the basic ideas of Bitcoin and G. We have 2 kinds of blocks. The first kind of blocks is key blocks that they bear the proof of work and they are valued 1 share. The miners add the key inside the block. And also the key block select a leader. So the miner of the last key block is going to be the leader of the consensus who is going to run the PBFT rounds while creating microblocks. Microblocks do not bear proof of work. They're created a lot faster. They're only created by the leader of the epoch, and they just include transactions. And because they're created only for 1 entity inside the system, they can be created a lot faster. And this is how we basically created our Bitcoin protocol. And we evaluated on DetaiLab, where we simulated up to 1,008 miners that were multiplexed on top of 36 machines. And in order to have a realistic wide area network, we imposed a 200 millisecond latency and a 35 megabps bandwidth per miner. These numbers are only for the miners. We do not care about full nodes and clients that are external to the consensus. The key questions we wanted to evaluate is, first of all, what size of consensus group can Bitcoin actually scale to? Are we to the thousands we want, or we are back to 20 like PBFT? And also, what is the max throughput that the system can handle? Is it 60, or it can get to 1,000? In order to compare our system with other approaches, we implemented a classical PBFT. We also implemented Bitcoin without using the tree to propagate, so we are using a star topology. And we implemented Bitcoin without the collective signing, so we have individual signatures that when the group consensus gets big, they take a lot of time to propagate and verify. So as you can see, the PBFT variant scales really bad. It couldn't even run with the 1 megabyte block, so it's only 250 kilobytes. The flat version of Bitcoin scales OK up to 150 miners, but after that, the links of the leader are completely saturated because he has to dispatch the block to everyone, and the latency skyrockets. On the other hand, both tree-based protocols scale a lot better. They scale the same up to 150 miners, but after that, the overhead of dispatching a lot of signatures and verifying them kicks in, and this is why the Bitcoin, which is the yellow line, scales better to the 1,000 miners, about 4 times less latency. On the throughput side, as you can see, even with the 1 megabyte block that Bitcoin currently has, even the flat version gets better security, better throughput. So we already have better security, and we get a throughput of around 8 transactions per second, which is a bit higher than what Arthur showed as the max for Bitcoin currently. While if we use the tree, we can get a lot higher, around 150 for the 1 megabyte block. And if we decide to increase the block to have higher throughput, we're going to suffer a bit in the latency. But for a 32 megabyte block, we can get close to 1,000 transactions per second throughput, while the latency for creating and collectively signing this block is around 90 seconds, which is a lot less than 1 hour. So, future work and conclusions. Of course, we have challenges that are ongoing in our system, and we would like to discuss. One of the questions is, what can the attacker do if he manages to get more than 1/3 of the shares? Maybe switch to the classical probabilistic consistency that Bitcoin uses until we can recover. That's a possible answer. Also, the system can currently only scale up, so we can increase the hardware of the miners, but we cannot scale out, like increase the miners, because then the performance deteriorates, and this is a problem that every blockchain protocol, that every node keeps the full state has. And of course, there are many discussions about splitting the state and sharding. And another small problem is that the leader is actually incentivized to exclude some miners from the consensus so that their rewards are burned and the value of the Bitcoin the leader holds gets a bit more. And I'm not sure how to solve it, but maybe we can just, instead of burn, donate this money to a well-known address of an NGO or something. So I have some questions that I've been already asked before you start asking questions. One of them is, what happens if someone gets more than 1/3 of the shares? And as I said, the answer there is that we're going to detect it, and then we're going to, okay. I first ask the questions. Second question is if we can have selfish mining in our protocol, because if we can have it, then the attacker can get more blocks inside the chain, which means more shares, which means more votes, and this is bad. Also, how is the consensus group size selected? Like, do we run it around 50 nodes, around 100, around 1,000, around 2,000? How many shares is it good to have? And finally, how do the miners exactly make money? So, surviving 34% attacks. What we're going to do is that we're going to detect that we cannot have liners, like we cannot create 66% signatures, and the leader is going to just release a block that's collectively signed with more than 51%. And this is already good, or even a bit better than Bitcoin, but it's not as good as the classical Bitcoin, and whoever verifies the blocks needs to know it, because we lose strong consistency. We can have forks now, but we can still continue in creating these 51% blocks, and after 6 confirmation, the proof of work is going to be enough, just like in Bitcoin. The window has to be shifted a bit so that everyone agrees on the consensus group. And also, in order to preserve the security of the clients, we're going to forfeit liveness at the microblocks if they cannot get 66%. So, second question is if we can defend against selfish mining with our protocol, and what I'm claiming is that our chain is almost fair, even under 34% attacks, even if the attacker has 45% of the computing power, because of the collective signature. So what we have is a block that is mined, it's announced, and it gets collectively signed. Next block is mined, it's announced, it gets collectively signed. So the selfish miner is going to mine his block, but he doesn't want to announce it because he wants to mine a hidden block. The problem now is that when he tries to he can't find the signature. So when he tries to create the new block, he needs to hash the previous block. But the previous block can only be hashed once the collective signature is appended on it. So the miner cannot create the target he needs to add in the header of the block to mine on top of it. So he better just release it because he has no gain there. Okay, another question is how we choose the window size. And because we don't have selfish mining, we can model our protocol as a random sampling experiment where the attacker has a chance of 0.25, for example, if he has 25% of the computing power to get one share, and we don't want him to actually get more than 1/3 of the shares. And as you can see, if the attacker has 25% of the computing power, we want more than 150 shares inside the consensus group, and in order to be really secure, we want 1 or 2,000. But if the attacker gets a bit more computing power for some reason, for example, 30%, then the 150 consensus group doesn't really work. It's only 83% secure. And we really need to have at least 1,000 shares, which corresponds to every miner in the last week. Finally, another question is how do the miners make money? And why do they participate? If they just make the money when they mine their block, then why would they stay for 1 week to sign the blocks? They can just mine for another altcoin if they are more incentivized there. And the answer is that they do not make money by mining blocks. They mine blocks and they get consensus group shares. They get money by participating in the consensus. So the Coinbase profit and the fees are distributed equally to the full consensus group. And the miner then is incentivized to stay alive because he profits more if he stays available for the full window. And he's also incentivized to keep mining because the more share he has inside the window, the higher percentage of fees and money he makes while he signs the block. Okay, so as proof of work, as future work, we also want to look into alternatives of proof of work, for example, proof of stake, because we have better security, so it might be easier to circumvent the proof of stake problems. We want to look into sharding in order to be able to scale out. We also want to incrementally deploy it to existing cryptocurrencies and see what are the actual problems of it. Like, we really want to model the system, the Bitcoin's adversary, and there is a great paper that was just introduced from the IC3 that I'm pointing you to look, and I really like it, and I'm going to try to model our system into this paper. We want to look into how exactly do the miners discover each other in order to create the tree. And we really want to see what actually happens if we get a 4% attack. So to sum up, we use collective signing and we managed to scale Byzantine fault tolerance protocols. We use proof of work in order to create a hybrid permissionless BFT. And we combined the above that increase the security with Bitcoin and G to also increase the throughput. We demonstrated that it is actually practical and it can be deployed. For example, for the 1 megabyte block, we can commit the transactions in 24 seconds and get around 150 transactions per second throughput. For the 32 megabyte block, we commit transactions in around 90 seconds and we achieve close to 1,000 transactions per second throughput. And also, because of the strong inconsistency, we can increase the robustness of Bitcoin. Thank you.
Questions? One here.
So I found your proposal interesting on a theoretical level, but how would you go about improving the security of Bitcoin's existing consensus system using your ideas?
The idea would be to keep having the consensus of Bitcoin, but optionally have collective signatures, so that if the miners manage to agree and create the collective signature of the 66%, or you can put it 80% if you want to be even more secure, then the client will know that his transaction is going to stay there after 1 confirmation instead of 6, as a first step. Then if Bitcoin NG is deployed, we can also increase the throughput there.
Other questions? No other questions. So, thank you very much.
Thank you.
And we go on with Mark Friedenbeck. with fast difficulty adjustment using a low-pass finite impulse response filter. Thank you, Mark.
Okay.
It doesn't have his last name on it, but
There it is. Thank you. All right, thank you for that nice introduction. For the YouTube audience, my name is Mark Friedenbach. I work at Blockstream Labs, but this presentation I'm giving is on work that was done in 2013 and was only now being presented. If there's any control engineers in the audience, I encourage you to go on Facebook. You're not going to learn anything here. This is mostly textbook engineering, but I'll be covering a couple of different mistakes that have been made in the industry with various alternative networks and proposals. Difficulty adjustment, as everyone knows, happens every 216 blocks. It's a very simple algorithm in Bitcoin. It basically just takes an average of the block time and adjusts so that if the same observed hash rate existed in the future, we would have a 10-minute hash rate in the next period on average. Very simple, very reliable, works really well, but is not responsive to sudden differences in hash rate or any catastrophic event that might happen to the Bitcoin network. So even though we can say that historically it has worked very well, it is because we've been historically limited to cases where the amount of hash rate differences that we've seen in a 2-week window is very limited. So we should be thinking about low probability events that could cause more damage and try to figure out both how much damage would happen and what kinds of things we could do proactively to prevent that in the future. So looking at where there's been a little bit more experimentation, such as alternative networks or altcoins, many of them see very fast hash rate fluctuation, sometimes increasing as much as 10x or decreasing by that amount in a very short period of time, minutes even, but typically within a day. And this is because there are multi-chain pools that will retarget based on profitability to whatever coin seems to be giving them the most money. And what these chains have seen is that they end up in a sort of vicious cycle where the hash rate is reduced, and not only does the opportunistic miners who disappeared go away, but also people who were mining on the platform go away because throughput is reduced, confidence is lost, and so on and so forth. So that's one thing that's been observed. Merged mine sidechains are still hypothecated. There aren't really any examples of merged mine sidechains, but nevertheless, one of the expectations is that with the current mining ecosystem, there might be a fair amount of difficulty in getting them secured and getting them kept from being vulnerable to these sorts of attacks, because if the merge mining is being done at the pool layer and a pool has, say, 25% of the hash rate, that might translate into much more of the merged mine hash rate, since not every miner is mining on the merged mine sidechain. Dropping that pool could drop by half the hash rate of the merged mine sidechain. And this can happen both because of a technical issue, or it can happen because of, for example, an attack. Like many of the attacks that we worry about with merged mine sidechains, the attacker has to stop mining the valid chain and start mining an invalid chain that takes all the funds. And that would be observed from the outside as if the hash rate suddenly dropped. And certainly we need to worry about, the success of one of those attacks for stealing pegged funds, but the problem is that if that sort of attack happened, the throughput of the sidechain itself shouldn't be affected. Things should still operate as expected. And finally, in the last point, this is one of those low probability events. If we have mining centralization, does not matter what country, but let's say right now there's 60 to 80% in China, what happens if there was some sort of major civil unrest and the Chinese authorities shut down access to the internet? This has happened, for example, in the Arab Spring. A number of countries shut down access to the internet. There's a couple of ways to mitigate that. One is to have the Bitcoin mining relay network use satellite phones and other technology that is less likely to be shut down in those circumstances. And another way is to adopt a adjustment algorithm that is more responsive to sudden drastic changes. So in practical terms, what might happen if a hash rate is reduced by 10x? That means that we would have 1/10 the transaction throughput. We'd go from approximately 3 transactions a second to 0.3 transactions. And in the worst case, if this were to happen right after a difficulty adjustment, it would take 4.5 months before that changed, because your standard 2-week window gets elongated out to 10 times as long. And as I mentioned earlier, this phenomenon has happened on alternative networks. It's been labeled a hash crash, and there's been many examples of it. Coins that has happened to, they often end up hard forking to another difficulty adjustment algorithm, although as I'll talk about later, they many times have their own problems. So the general suite of solutions that are available, we can adjust more frequently. Why 2016 blocks was chosen for Bitcoin is a little nebulous. It's extremely conservative. As I'll show later, it is actually so conservative that it is perhaps a suboptimal choice. And we can, relatedly, there's no reason why the number of blocks that you look at for an adjustment has to be associated with the adjustment interval. Those are almost the same in Bitcoin, not quite the same, and there's a bug because of that. But there's no reason they even have to be that related. And finally, what most altcoins do is they change the control algorithm. And so there are some good things you can do in that area. There's also some very bad things you can do in that area as well. So I'll spend a little bit of time to talk about this slide, since I have, I think, 3 different charts that look like this. And unfortunately, none of you will be able to read any of the axes on here. I apologize. But what you're looking at is the effectiveness of a difficulty adjustment algorithm run in simulation for various sized intervals of adjustment, and both the sliding window and the interval for adjustment, using the standard Bitcoin adjustment algorithm. So the far right-hand side of the graph is about 2016 is the furthest point, and that's when you're adjusting every 2016 blocks using 2016 blocks worth of data for the adjustment. And the y-axis of this chart is an error metric. So what we do is we run the simulation for 20 simulated years, and then we build a histogram of the actual observed block times, interblock times, and compare that with what is the expected histogram given by the probability function. And so lower is better. Lower means less error. And the first thing I will call your attention to is the sawtooth pattern. That's just simply because what's being simulated here was a square wave hash rate where we went from 10x to 1 and back up to 10x. And the sawtooth pattern you're seeing is just when certain intervals line up with the difficulty adjustment algorithm. So I'd ignore that, and I'm going to focus in on the area that doesn't have that sawtooth analysis error. And so what you see here on the left-hand side, and well, I'll focus on the right-hand side first. We have this kind of linear relationship where as you increase the size of the difficulty adjustment interval, you get more and more error, mostly because you're not reacting fast enough to any sudden shifts in the hash rate. And on the left-hand side, we see a different error that's going on. It's actually a confounding of 2 separate sources of noise. One is that because in this simulation I've linked the sliding window size to the adjustment interval, as you get shorter and shorter, you're taking into account only 10 blocks, and then you're only taking into account 5 blocks. And so you start reacting to sample sizes that are not statistically significant. But it turns out even when you subtract that out, there's still underlying error due to the fact that if you're responding to a random variable and it has variance, and you're responding really quickly, then you end up shooting, overshooting or undershooting by quite a bit if you happen to have a couple of lucky blocks in a row or unlucky blocks. And it's worth pointing out, not to dig or anything, but a number of the coins that are considered to have the better difficulty adjustment algorithms, they adjust every block. And if you adjust every block, it's actually not even shown in this chart. It would be somewhere through the ceiling, far off on the left-hand side. It has a tremendous amount of error just from that variance effect. And then now we've zoomed in on the elbow of the curve, which is the sweet spot. So if you're using the Bitcoin difficulty adjustment algorithm, you get minimal error if you're adjusting somewhere in the range of every 30 to 50 blocks. Small aside, so when the point is raised, well, maybe Bitcoin should have adjusted a bit more frequently. The often first point that is made is that some attacks, such as the time traveler attack, for example, become more easy with a smaller adjustment window because your effectiveness is larger. And this is because the timestamps on the blocks are very loosely constrained to be related to the actual wall clock time when the blocks are found. Miners are allowed to lie within about 2 hours of when their block is found. And so if you have a given function for calculating the hash rate, the miners will be able to choose blocks that will then create lower difficulty periods. But that said, as long as the window that you look at is at least as big as the adjustment interval, then they're unable to actually lower the difficulty rate on average. You can lie and lower it for one period, but effectively you've raised the period after that by the same amount. And so as long as you're adjusting frequently enough, you're not going to see any kind of rapid oscillation. But nevertheless, if you consider systems quite different from Bitcoin, you can run into this problem, so you have to keep it in mind. And so if we were to choose, like in this example is like if we choose a window size of 36 blocks, which is about 6 hours for adjustment, you can then say, well, okay, well, how frequently, if we're looking back 36 blocks, how frequently do we want to adjust? Because we could still adjust every block, just looking back 36 at a time. And this chart shows that on the right side is 36 because you don't want to get larger than that or you'll have the time traveler attack again. And on the left-hand side, again, I've clipped it, we don't go all the way to 1. But it turns out you get a very rapid exponential increase. So if you're adjusting every block, you again have that same variance problem. And it turns out that with a Bitcoin-like adjustment algorithm, if you're adjusting about anywhere less frequently than half the size of the window you're looking at, then you're okay. So if you're looking at a 36-tap sliding window, then you can adjust, every 18 blocks, for example. Interestingly, and this is a little inconclusive, if you choose a longer adjustment window, like say 100 or 1,000 blocks, you can actually get a lot closer. So this rule of thumb I just gave you is really talking about if you're trying to minimize the sliding window so as to have the fastest reaction time and lowest error. Okay, so that said, we were just looking at the Bitcoin adjustment algorithm, but it turns out that the Bitcoin algorithm is suboptimal and known to be such. You can look in the control theory for problem. There's a lot of literature describing this kind of problem where you have some variable. In this case, it's hash rate, which we're sampling, but we have we have exponential random noise that is added to our samples. And what we want to do is we want to figure out what the general trend is and respond to that larger trend, ignoring the kind of random fluctuation. Well, the term for that is a low-pass filter, and you can look in the literature and you can find for a first order or for a second order control algorithm, you can find the optimal filter. In this case, I've given on the bottom a Python code for generating an optimal first order filter using the Parks-McClellan filter design algorithm, which I've illustrated on the next slide. It's basically a linear weight that you apply to the inner block times that will result in an average, which you can then use that is going to be more likely to be accurate of the actual underlying inner block time than the straightforward naive average that is used by Bitcoin. And so what you're seeing on the top here is just plotting the weights themselves. So you can see that not all block times are being treated equally. The middle of the interval is given extra weight, and there's actually periods on the side that somehow are given negative weight, meaning that a longer block time would make you adjust in the opposite direction. But this is just an interesting characteristic of how these sort of filters work. The bottom graph is a semi-log graph, and the y-axis is log in the y, showing the frequency response for that filter, which shows that the low frequency filter, the low frequencies, which represent the long-term averages, are passed through unchanged, and the high frequencies, which are where that rippling is occurring. Again, this is a log plot, so those are actually a factor of 100 less, and they get severely modulated. And so any kind of like random variation that's block by block is just canceled out by this filter, and you just kind of see the long-term average with a little bit of long-term noise. And this adds in two more parameters which are tweakable, the gain and the limiter. So if anyone who's doing this kind of analysis for your own network, this adds in, so you have a total of, I think, about 4 to 6, depending on how you count free variables to be minimized. The next slide is empty, but I do have a little bit to talk about before I go to questions. And that's mostly about applications. As I said at the beginning, it would be very interesting to apply this technology to a sidechain, an emerged mine case, or alternative networks that are doing kind of non-currency schemes. And in these cases, you have to be very sensitive to, there isn't kind of a one-size-fits-all solution. You have to be a little bit more sensitive to what goals you want to get out of the system. Because a short interblock window might have more variance, which means that you'll be adjusting more frequently, and you'll be sometimes overshooting and undershooting, but you'll be responding very quickly to a large hash rate change. And if you're expecting that, or if that's in your threat model, that potentially your sidechain might get attacked and you need to respond quickly to be able to get something on chain, then you'll want that, versus a longer window, which will allow a little bit more oscillation, but it'll be more accurate as well. And so it's not easy. There are functions you can use to just minimize, optimize a multi-parameter system like this, but it's not easy to define what the utility function for that should be, because it kind of depends on your scenario. This particular filter that has been demonstrated here has been used in FryCoin for the past 3 years and has been very effective at eliminating the multi-pool hopping. It's still there, but like it barely has an effect really on the system. And with that, I'd be happy to take any questions from anyone.
Thank you.
Very simple question. I didn't catch where you said that this system has been used.
Yeah, so FryCoin, it's an altcoin, and it uses a variant of this. I think there's a couple that are derived from that. For the most part, the other systems like Zcash and Ethereum both do an immediate response to the last block. So based on the time between the last block and the next block, they do an adjustment, and it's a nonlinear adjustment, but it is basically kind of a weak approximation of this, a little bit more noisy. And so they fall on the very left-hand side of the curve when I was showing where it kind of spikes up to high error rates.
There?
Hello.
No.
Yeah, here.
Okay.
I just wanted to add that the faster difficulty adjustment also changes the incentives in selfish or stubborn mining attacks, as Arthur showed in his presentation, that if you don't change the difficulty adjustment, a selfish mining attack may not even gain any profits, but in the original paper, I think the assumption is that kind of the change is immediate, because then you lower the difficulty and get more profits by pretending that blocks that you don't, are showing less work than you actually do. So this is just another important point to consider.
Are you saying because you'd be capturing more subsidy in that case?
Yeah, I think the idea of the selfish mining attack is that you increase your relative hash rate as compared to the other miners, but of course this only takes an effect when the difficulty is adjusted. If the difficulty were constant, then your relative hash rate doesn't matter. If it is adjusted basically immediately, then this is all you care about. In reality, you kind of care about something in between, because the difficulty adjusts after 2 weeks, right?
Yeah, that's partially true. I think that the largest aspect of that is simply it's not the time traveler attack, but that's all the word that we have for it. The fact that the Bitcoin adjustment is longer is you considering a period that's shorter than the length of the adjustment cycle.
No, that's one attack. I think it's a different. It's just you have to think about the incentives for the selfish mining
Right. You
attack,
certainly
basically.
one of the issues, and perhaps this is where you're going, is that if you allow large variation in your difficulty, then one of the things that you can do is you can temporarily allow a much shorter interblock time by unfairly adjusting downward. This will be counteracted later. When you adjust later, it'll compensate. But during that time period, you can take advantage of the selfish mining properties and use the fact that you're mining your own blocks to have an advantage over the competition. But I believe the effect of that is quite small.
There.
So in your plots, you've got a minimum around 30 to 50. What sets that minimum? What parameter causes it to be 30 to 50 and not 3 and not 300?
I think, honestly, I'm not sure what the theoretical underpinning of that is. I mean, this is a experimental result. I can explain why you have noise to the left and noise to the right, and I think this is just when the two noises, are minimal. On the right-hand side, it's because you're adjusting too infrequently, and so keep in mind these simulations have large spikes in the hash rate, and so because you're adjusting really infrequently, you have a large error rate because there's a long period of time before you adjust. And on the left-hand side, because you're adjusting so frequently, you have a lot of variance, and that kind of spreads out. Your expectation is still that you would find that you would settle around the right hash rate, but you would be oscillating so much that you wouldn't have consistent difficulty representing the underlying hash rate.
Okay. I mean, just in general, there's always some parameter that should allow this minimum to move around. I don't know what it is. Secondly, the engineering literature has another solution to this, and that's the critically damped harmonic oscillator, which is shock absorbers.
Right.
If you know the oscillation, or at least in this case, if you have your sliding window or the block time, both of those could set essentially the maximum rate at which somebody could slew the hash rate around.
Right.
And so that can set the oscillation parameter, which can be used in a critically damped harmonic oscillator, which essentially is the optimal solution to this. A low-pass filter has an additional parameter, and that is what frequency below which we're going to discard things.
Thank you. I skipped over that, yes. That was an arbitrary number that I had on this slide on the bottom. So I mean, the linear filter is obviously it's a first-order correction, and in the literature, the optimal one is a second-order critically damped harmonic oscillator. Yes.
Thank you, Mark, for a great presentation. So I'm not against the adjustment, and I'm not against the low-pass filter, but you said during your presentation a couple of words which creating like drama about possible switch off the hashing power and so on. In real world, it's working a little bit different. So if some of a miner will go down, the other miner can adjust the frequency. It's consume more electricity, but they can generate more hash power, and it will provide a lot of compensation. So it's meaning for some of a miner, it can even double or triple the hash rate. So it will be bigger power consumption, but just believe us. So if 1/4 part or 50% of a miner will go down, the other will be just economically pushed up to generate more profit. It's in their interest. The second one, thanks to, he also said there is a lot of hashing power was located in China. So no, this is not the truth. So there is a lot of pools, but there is a lot of customers outside, and even, and Jihan from Bitmain, I think, they can also confirm, they have also the data center in US, and there is a lot of power located outside. Mm-hmm. So just the location. And also, if something happens, which some biggest pools, so users can switch their hash power for another pool. So it's more flexible, but still, this is great adjustment, so we can do it, and any improvements will be great. But no dramas.
Thank you for the corrections.
The one, Christopher?
Yeah. I had a question in regards to, one of the other oscillations that happens on Bitcoin, of course, is the halvenings. And different altcoins have different approaches to that as well. Has there been any, if you looked at the intersection of this oscillation with the block rewards changing as well, and is there a timing or optimization there?
Unfortunately, in both halvenings have been preceded by a run-up in price that compensated. Some people think those are causally related. I think it's coincidence, but nevertheless, we don't have good historical data because mining was suddenly twice as profitable, and then you got half the return, and it evened out in the end. The charts I did in the beginning were assuming a 10x difference in mining, so that this should illustrate the same sort of phenomenon that's going on. Thankfully, only halving, I think, is, as Alex was saying, it's kind of within the range of if it halved and it became suddenly unprofitable for some and they turned it off, the others would be able to make up the difference, and even if they didn't, it would only go on for a month. It's more the catastrophic scenarios that I would worry about with respect to Bitcoin that are like on the range of like 5x to 10x or more. The question was, what about for side chains? Side chains, it's a similar story. It's more exaggerated, at least with the current system, because the Bitcoin is the gold standard in terms of decentralization. And if you have a merged mine side chain, it is only likely in practice to be less decentralized than Bitcoin itself. Since you would imagine all the large pools are doing it to get money, and it's a question whether or not the independent hashers would be doing it.
Last one.
Mark just got the correction from Jihan Wusu. They have 42% from outside of China. So
From
it's
outside of
meaning,
China.
yeah, it's
This is
meaning,
Bitmain specifically.
yeah,
Right.
Bitmain specific. And I think the other pools, it's approximately, so 30%. So it's really distributed power.
Right, right. And I did not mean to pick on anyone in particular with that. I'm just pointing out a possible scenario. I mean, you could substitute any other country. There's a possibility if electricity prices in the Pacific Northwest continue to decline, that all this might get relocated to Oregon and Washington State. In which case we would have the exact same problem if the U.S. ever had issues.
Thank you very much, Mark. Thank you. Okay. Going on breaking the chain, another interesting alternative implementation after we have seen Bitcoin and G. This is not just an interesting what if, but also maybe an inspiring idea to some changing in actual Bitcoin. David Dvorak will present new braiding techniques to achieve significant scaling gains. So, let's go. Thank you, David.
Oh, great. Okay, hello. So my name is David Dvorak. I've been with Bitcoin since 2011, back when the price was like $1.50. And I've been a full-time blockchain engineer since about 2014. And I run an altcoin for decentralized cloud storage called Saya. So I've been around. And today I'm going to be talking about braiding, which basically means we take the straight line blockchain of Bitcoin and we make it so that blocks are allowed to have multiple parents, and you get graphs sort of like the one presented. So we get consensus by either picking a set of blocks to choose and deleting the rest, or we apply a sorting to the blocks that we have. And so inclusive means that you take blocks into your chain, into your like final post-process chain that have conflicts. And so what I'm presenting today is going to be an inclusive braid. So why would we want to do this? I think that the biggest reason would be to get rid of selfish mining and to get rid of orphans. And so today with Bitcoin, you have this effect where the latency between when a miner finds a block and when the miner can tell everybody else about the block, everybody else is mining on basically an old block. And this is sort of lays the foundation for selfish mining. Large miners, large hash rate miners can get advantages from this latency. And basically you get more profitable per hash rate as you get more hash rate. And that's a centralization pressure, and we would like to get rid of it. But you also have like throughput issues where Bitcoin, things are idle for 10 minutes at a time, and then you have this like very short window of high burst activity, then 10 more minutes of idle time. And so we'd like to bring down the block size or block time. That way we can get more optimal throughput. Sometimes in Bitcoin, confirmations can take up to 30 minutes. And so if we bring down the block time, we can have more consistent confirmation rates. And then finally, we get more miner payouts. If you bring down the block time, you get, say, 400,000 payouts per month instead of 4,000. And that's good for solo mining. Right now, if you want to solo mine, you need hundreds of thousands of dollars, if not more. And if there are 400,000 payouts per month, we take that down, so you need thousands of dollars to solo mine. And it's much better for decentralization. So there are a lot of non-braiding solutions to some of the problems I mentioned, such as the relay network and fiber, or like weak blocks or PETA pool, which take care of some of the throughput stuff. But a lot of these solutions either they don't eliminate the problems entirely, or a lot of times they don't stop miners from making intentionally malicious blocks. And so they fail during adversarial situations. And I don't think we really have a good solution to selfish mining at the moment. And I'm aiming with this to fix selfish mining entirely. So there's existing braid work. Bob McElrath presented in Hong Kong. Then there's stuff like Ghost and what Ethereum runs. And then the creators of Ghost have some more recent work as well. What I'm doing is pretty different from a lot of what's been presented so far. So basically, I tried to make it as easy to understand as possible, especially like the security parameter. Make it, provable that 51% attacks, or you can't reorganize history without 51% of the hash rate. And then just for some context, as I start talking through things, the block time is going to be around 6 seconds. The block size is going to be around 50 kilobytes. And that's just for context when I start, throwing numbers out. So with the block time of 6 seconds, you get a much wider graph on your blockchain. In Bitcoin, if you just freeze the network at a random time and look around, on average, every miner is going to have seen every block. When your block time is 6 seconds, if you freeze the network at a random time, usually there's going to be a block or two, or sometimes even like 6 blocks that haven't been seen by everyone yet. So when miners are sort of pointing at each other's blocks, you get, and the graphing software I was using just would not draw this graph for me. So I drew it by hand. You get this crazy mess where some blocks are including each other, and it's one paper called it a tangle, which I think is pretty fitting. You have confirmations going every random direction. So I want to step back and talk about the security a little bit, and things you need to do if you're going to be a credible replacement to Bitcoin. And so the most important thing that Bitcoin does is that history is immutable. If something has 1,000 or 2,000 confirmations in it, I don't think anyone is going to bet money that history is going to be changed or altered or reverted. And so you really need that to stand. That's like the one thing that makes Bitcoin worth looking at. But Bitcoin also has this 51% barrier where anyone who is less powerful than half the network cannot engage in history reorganizing activities, or just can't do malice. And so that's a very high bar, especially because most Byzantine protocols can only get to about a third. So you want to keep the 51% bar. SPV is something that our ecosystem has become really reliant on. And so initially when I was working with this, I was just like, we'll throw away SPV. I realized later that that was just too much to do. So you really need to support SPV. And then finally, two things that Bitcoin does not really do well is that you should not, as your amount of hash rate grows, you should not be making more money per hash rate. And then as your networking gets better, you should also not really, it should not be highly profitable for you to have a much more expensive network. And so some things that you have to watch out for are denial of service attacks, and especially when you start messing with the, with the shape of the graph, transaction fee considerations. People can play around with transaction fees in malicious ways, and then double spend attempts. So, yeah, just to spend a little bit more time on the double spend attempts. When you're including all the blocks, what that means is that double spends are free. And so in Bitcoin, it's actually not that hard for like a 25% miner to reorganize 6 confirmations of history. I think that if they're trying, it's something like 5 or 10% chance that they'll be able to do it, which is really high. On the other hand, if they hit that 90% chance that they fail, they're going to lose however many blocks they mined, and that's a lot of income to lose. But with an inclusive blockchain, you don't lose that income, and so it's not as scary for a miner to attempt it, and the success rate is actually really high. So it's something that you have to be aware of and you have to address if you're going to make an inclusive blockchain protocol. And so, yeah, like I said earlier, we really want to try and make it so that if you have not that much hash rate and you're in a remote area, or maybe you're even mining over Tor, and you're a really high latency miner, that your profitability matches someone who's pouring millions of dollars into a data center. And so we include blocks. They're going to be conflicting blocks, and in Jute we handle this by, instead of throwing out blocks that hurts miner profitability, we'll pick the transactions that are invalid, and we'll throw out the invalid transactions per block, keep everything that's valid. Okay, so now to the more fun part. So consensus is built in Jute by looking for a main chain in your graph. And so essentially, when a block happens, it looks at the history that it's confirming, and it finds a main chain, and then it confirms the main chain only. And from that main chain, you sort of derive a total sorting. And so the main chain is sort of, you can think of it like votes. You have edges from blocks, and I think I'll go ahead to the picture. So here we have a very small chain. We have blocks 1 and block 2, and they're each confirming the genesis block. They confirm their own edge. To them, there's only one chain, and so that edge has 1 vote. When 3 merges it, 3 is going to have to pick between them somehow, and we'll get to that later. And then 3 will confirm just one side of it. And so whoever it picks, he'll cast his vote to that, he'll cast his vote to himself. And so you get these edges in the graph that start to gain votes. And so when all the other blocks follow this algorithm, we see that initially the 1 and 2 were tied. And then over here, we have the edge from 1 to 0 has 5 votes, the edge from 2 to 0 has 1. And so if you want to change the direction of the main chain, you're going to have to put 4 confirmations on block 2. Meanwhile, the entire rest of the network, the honest half of the network, is increasing the confirmations on this one main chain only. And so that's how we get the 50% assurance. So tie breaks. So what we do is first we check and we see if they have the same number of votes on an edge. We see if one of the children has more ancestors. In this case, they don't. So when they don't, we just use the hash of the merging block to seed a random number generator, and we pick randomly. And this can have consequences, but they're not that severe, and it's like a simple thing to do. So here I have another example, and it's just to show again. You see the main chain follows this line, 0 to 2 to 4 to 7 to 8, and then when we add more confirmations, we add a tail. That main line gets much stronger. Meanwhile, everything else stays at 2s and 0s. Cool. And then I wanted to show what happens if you never have the chain come together to a single point. You still get this edge up here still gets very strong. So this graphing algorithm is not reliant on things collapsing together. You can have a very wide graph that is perpetually wide, and you still get your security. Okay, so I kind of went over this a bit already, But if you want to reorg the chain, you basically have to favor an edge. You have to pick an edge, and then you have to mine blocks off that edge where none of those blocks have any of these blocks in their ancestry. And they have to get up to 14 confirmations. And then you can move the main chain, but you're fighting the entire network, all of the hash rate. So you're going to need 51% hash rate to execute this, this reorganization. Cool. So I'm just going to skip the almost part. You can read the slides, but I don't have enough time. Pardon. If you make the block time too low, you actually lose this convergence property where it's dependent that on one side of the, if some miners are mining on, you say 3, and some miners are mining on 5, at some point they have to agree that either 3 is heavier or 5 is heavier. And so if you have like a split, like a bottleneck, like the Great Wall of China, where blocks tend to move really slow, you bring the block time down really low. You can get one side of the chain has more confirmations, and if you freeze the network and look at everything, one side is winning. But by the time the rest of the miners know that that side was winning, they've mined more blocks. And so you could have an attacker who doesn't have that much hash rate, who can find like this balance, this like center point, and can just distribute hash rate to each side and keep them balanced and sort of prevent the network from converging. So that's why I set the block time at 6 seconds. I would really like to bring it lower. I think there are a lot of good things that happen if you bring it lower. But there's this convergence attack. We get an attacker who can stall consensus probably indefinitely and at least commit censorship or whatever. And so that's, I don't know how to fix that solution without introducing like weird backbendy things that just don't seem good. Okay, so I've talked about how we find the main chain. Now we need to know how to sort the blocks that aren't on the main chain. And so the first thing we start with is that no parent should be, in our final ordering, no parent should come in front of its child. And so for each block in the main chain, you start with that block, you include all of its ancestors that aren't in the chain yet, and then you go to the next block in the main chain, you include all of its ancestors. And to pick an ordering from its ancestors, you sort of do a mini main chain. So just to walk through it really quickly, we're going to start with 0, then we're going to go to 2, because that's the next block in the main chain. There's no ancestors in either of these, so then we're going to go to 4. Then we're going to grab 1, and what we're going to do is we're going to look at the chain as it was when 4 was created, and we're going to organize the blocks by edge weight as 4 saw it. And this is really important because it means that because we're looking at it how 4 saw it, adding things in the future cannot change the ordering of these extra blocks. And so the only way with this algorithm to mutate any of the past history is to modify the main chain. And as we've shown, it's difficult to modify the main chain once convergence has happened and once enough confirmations have been put in place. So yeah, this just walks through each block in the main chain and how the sorting algorithm operates. So I have code for this. All these blocks were generated by code. You can check out the GitHub link. Yeah, and I guess I'll let you guys explore that. So there are 3 really big problems that come forward when you start doing this. The first is that transaction fees work entirely differently. If 2 blocks mine the same transactions at the same time, and with 6-second block times, this is very likely. Some of those transactions are going to have to be thrown away. You lose throughput on the network. The miners are losing their transaction fees. And so you have to take a probabilistic approach. I don't think I'm going to have time to go into it. But basically, the whole transaction fee landscape is completely different. Second is that if you're fully inclusive and you allow blocks from infinitely back, you can have miners who just withhold blocks and don't announce them for say a month or 2 months, and then all at once they just drop 500 blocks on the network, and the network gets this huge congestion that it has to sort through. And then finally, I kind of said it earlier, but if there are no orphans, that means that double spending is cheap to attempt, and double spending is pretty easy. It's just that in Bitcoin, it's also pretty expensive, and so nobody tries double spend because miners like making money. So I'm just going to skip over the transaction fee stuff. All right, 4 slides, 5 slides, cool. So for the denial of service attacks, what you get is you get an attacker who can, mine over like 2 or 3 months, get a ton of blocks, drop them all at once. To stop this, what we do is we say if you're more than 200 blocks behind, we won't count you in the chain. And so this actually opens up a window to cause orphans. If I'm a malicious miner and I can get my 200 blocks in front of the rest of the network's 200 blocks, which is this is a probabilistic thing, then I can cause orphans on the rest of the network. So, oh, I lost my place. So we want to make sure that the amount of damage that can be done by an attacker who is lucky enough to get 200 confirmations deep, which is maybe 1 in, I forget, it's like 1 in 10,000 chance. With 400,000 blocks a month, a high hash rate miner can do this pretty frequently. We want to make sure that the damage is not very high. So what we do is we allow the headers to still be viewed by the graph. So you disregard all the work in the blocks that are 200 behind, and you disregard all the transactions. But if there are blocks that depend on these, on the blocks that you've invalidated that merge these, you allow those blocks to be included. So if an attacker manages to get 200 or 250 blocks ahead, gets to displace 250 blocks, instead of the honest network losing all 250, they only lose 50. And so this is not ideal, but compared to selfish mining in Bitcoin, the amount of profit that even like a 45% hash rate attacker can gain from doing this, trying to push orphans through the denial of service prevention mechanism, is very tiny. So at 200 blocks, it's sort of an acceptable change. Okay, so the really important one is double spends. And so double spending out to 6 confirmations, especially if you have like 40% hash rate, is really easy. And especially because there's nothing stopping you, it's a big concern. But I'll also observe that trying to brute force a private key is really easy. Each attempt does not take very much energy. Your computer can do hundreds of thousands per second, or maybe only thousands per second. But if it's an 8-bit private key, it's going to be trivial to break. And that's why in Bitcoin we use much larger private keys, such that even though each attempt is trivial, getting a full real Bitcoin private key is something that's just completely impractical. So in Jute, we do the same thing. Instead of waiting for 6 confirmations, we want to wait for 50 confirmations or 200 confirmations. And since the block time is 6 seconds, that's actually not so bad. 50 confirmations takes 5 minutes. And I wrote a simulator, which I'm not 100% confident that it is a correct real-world mapping. But I wrote a simulator for attackers who try to double spend. There's some parameters such as attacker hash rate and network latency. And the results are posted in the repo. But it basically says that if your threat model assumes a 33% hash rate attacker, you're going to want to wait for 50 confirmations. At that point, there's less than a 1 in 1,000 chance the attacker can reorg the chain that deep. If you're assuming a 45% hash rate attacker, it actually gets a lot worse. You have to wait for 500 confirmations. And this gets much worse as you approach 50% hash rate. And then obviously, once you're above 50%, no amount of confirmations can keep you safe from a 51% attacker. So I'm going to go ahead and skip this slide, and I'm going to talk about SPV. So how do we do SPV in a chain where when we merge the blocks, we're going to be throwing transactions away out of the block? So if the block is just committing to itself, and then that there were merge conflicts, the block didn't make it into the main chain, you're not sure which transactions in that block may have been thrown away. So instead what we do is we have the block commit 200 blocks back, which, if you remember, is the same number as the denial of service window. So if the reorg is more than 200 blocks deep, it's invalid. And what this means is that when you're doing SPV, the SPV nodes can draw the graph. It's very easy to draw the graph and not download or verify any of the transactions. They know out of those 200 commitments that the block made, they know which commitments are invalid. And so if there's a reorg that went 80 blocks deep, they know just to ignore those 80 commitments and take the commitments from deeper back. And they wait for more confirmations so that the future blocks are committing to basically the correct transaction set. And so in doing this, you can sort of recover SPV, and you also give the SPV nodes a lot of flexibility in deciding whether or not they want to accept a transaction at 10 confirmations or 50 or 500. You leave that up to the implementation. I'm going to skip this because it's only relevant if you bring the hash or if you bring the block time very low. And like I mentioned, due to the convergence issue, can't do that. So you need this to get the block time low, but it's not sufficient. And then here's more hand-drawn graphs that we can admire. All right. So just to reiterate the weaknesses, I'm going to lead with the weaknesses. Bitcoin has really strong counter incentives against miners attempting double spends. You end up throwing away blocks, and because you accept blocks from very deep, even at 200, you can have a miner who's got 33% hash rate can mine 66 blocks in that window and then dump them all at once. So you have this network that's subject to basically trivial flooding up to some limit, and that limit's not so severe. And then attackers can stall consensus even at 6 seconds. They have a limited ability to do it, but if you go lower than 6 seconds, they have much greater ability to stall consensus. And then finally, this is like completely new territory. I'm sure there's a lot that hasn't been covered, and so you wouldn't throw this into Bitcoin tomorrow, just because there's a lot of unknowns, just because it hasn't been looked at very much. But the advantages are that we get rid of selfish mining, we get rid of orphan blocks. For the most part, we make mining fair regardless of your latency or your hash rate. And I skipped some stuff on the transaction fees. So low latency miners still kind of have an advantage due to being able to see which transactions have been mined faster than everybody else. But this is less significant than the selfish mining situation in Bitcoin. So the reduced emphasis on latency means that network optimizations can focus more around throughput. And then the larger number of blocks per month helps solo mining. And then finally, a safe number of confirmations, if you're assuming a 33% or a 40% hash rate attacker, means that confirmations happen in between 5 and 15 minutes. And the variance on that is very, very small. So I believe that I got to the end. 10 seconds to go.
We only have time for one question. I'm sorry. We are already late.
In other direct acyclic graph designs, such as Altcoin, Tangle, or Byteball, the block is actually one transaction. But in your design, the block has many transactions. And what usually happens is that those blocks that are competing have the same transactions because transaction propagation is faster. So how you address that, or what are your thoughts on that?
Yeah, so I did skip over this entire section, but basically you want a sort of deep mempool, so maybe like 20 or 30 minutes deep. And then what you do is the miners, instead of mining the highest fee transactions, they mine probabilistically. They mine random transactions weighted by how much the fee is. And so if you have, if we take this out to infinity and you have an infinitely deep transaction pool, the miners randomly selecting transactions will never have any conflicts. And then, obviously the reality is that your transaction pool is not infinitely deep. But if it is deep enough, then the amount of conflicts, or the amount of throughput you lose to conflicts is very low.
Thanks.
Thank you. Thank you very much. Now, last speech before the workshops, presenting progress on scaling via client-side validation is Peter Todd. Thank you.
Howdy. So, yeah, let's go and start off with really kind of a short intro to, what isn't client-side validation. And I'm going to kind of call this the miner-side approach. This is actually some Ethereum smart contract code, and I took a look at some of the stuff to kind of get a bit of an overview of what they've been kind of doing, because they often kind of go in the opposite approach here. And this example is Chronos, which is a timestamping contract. And basically what you have here is a contract that stores in the Ethereum state consensus hashes as they're received and timestamps it, puts a timestamp. And ultimately, at some point in the future, I guess in theory, you can go and ask the Ethereum state machine, when did you go get this hash? And, this is kind of typical of, I think a lot of these applications, and it does raise a lot of questions about, who has the data? Do we really need so many people to have the data? In comparison, client-side validation of data is actually probably the mainstream thing that happens. This example here being my bank. And when you ask yourself, what's going on under the hood? Well, my web browser starts off with a root of trust. It's receiving signatures from a server that I don't trust originally. I go check those signatures, all in my client. Eventually, I get to the part where a green bar displays, and then I download the rest of the website. And that's actually pretty typical, There's no shared consensus. It's all done client-side. This is pretty much how most crypto is actually implemented. Things like Ethereum's, let's put into the consensus state machine, that's sort of the unusual approach, and it's something I think we've kind of maybe done a little too much in kind of this so-called blockchain world. And if we're going to talk about, well, what do we have in our toolbox to do these kind of client-side protocols, it's actually fairly simple in many ways. Your basic primitives are essentially signatures, which of course is what pretty much everything in crypto relies on anyway. You've got proof of existence, in that I'm showing that something existed through a series of hash operations to some chain. And yesterday you probably heard Ricardo go and talk about timestamping in general, so I won't cover that in too much detail. And then proof of publication. And that one, the last one's a bit of an odd term, because what we're really saying here is, whereas, say, timestamping is I am proving that a particular message existed before a certain time, in proof of publication, I'm proving that some message was added to some set of messages. I'm proving that if someone else wanted to, they would be able to go find that message, or alternatively find that it didn't exist. And we'll see in a second how that gets used. But case study, open timestamps. Well, example of my timestamping thing, Ricardo mentioned it, and I think the key takeaway here is, well, if you ask yourself, how much data does the whole world need to have in consensus? It's very small. It's just the Bitcoin block headers, essentially. So this scales very well. I'd consider this type of proof a solved problem. There's probably going to be a lot of bike shedding over exactly how do we create these timestamp proofs, but I think it's pretty clear the general approach to take. So, we have that in our toolbox. Another case study, Blockstack. They're using our final type of proof, the proof of publication. Now, I'm sure the Blockstack engineers in the room here will yell at me for oversimplifying, but essentially you can say that it takes the blockchain, it starts at some point in the past, reads through it, and because everything is in consensus about what data you're applying this algorithm to, being the Blockstack consensus algorithm, we can guarantee that we will get the same result. And in Blockstack, if I want to go and register a domain name, change something about my domain name, etc., essentially all I'm doing is publishing part of the data relevant to that operation, to the chain, that guarantees that everyone else will receive that data because the proof of publication guarantees that they can read it, and their consensus algorithm will run through, hopefully get to the same results. We'll see some caveats in a second there, but this works. This is being implemented. Blockstack is one user of it. Counterparty, Mastercoin, or other applications of this doing it in slightly different ways. And again, I think there's some engineering constraints here, but we can say this is a valid approach and it does work, which leads to maybe an interesting question. Could we do this in Bitcoin? And we often hear people say miners are validating blocks. Well, if miners are validating blocks, what's your full node doing? Because your full node's also validating blocks. And if miners didn't validate blocks, what would your full node do? Well, it would validate blocks. So imagine if we changed the Bitcoin protocol rules and we just said, well, you've got this proof of work thing. You've got this consensus over what is the most worked chain. We'll keep that part in, but we'll say what's in that chain could be anything. Your full node will not reject a block under any circumstances, regardless of what's in it. Maybe we'll say, less than 1 megabyte or less than 10, depending on what camp you're in. But ultimately, the contents of the block, we won't reject it on any basis. However, if I want to send you money, because you're running a full node, your full node can go through the blockchain, reject all the stuff that doesn't follow the protocol, and assuming we are in fact running the same software on both sides, and there hasn't been a bit flip or something like that, you and I will come to consensus. And when I send you money, it will pop up in your wallet, and then when you send me money, it will pop up in my wallet. That works. So really, you can say miners validating is actually kind of an optimization. It does have some interesting social effects about, what is the valid definition of a Bitcoin. After all, if we had this rule, I could also create Litecoin, and Litecoin and Bitcoin could coexist on the same system. And that raises social questions, but it doesn't really raise technical questions. Technically speaking, this can pretty clearly work, although it's going to be fun trying to figure out which currency you want to pay miners in. So if that's true, then maybe we've got to go and look at, what is this double spend problem? What's so hard about it? And I like to use the analogy of where's Waldo, which is, well, you've got this big pile of block of space, and you're trying to go find Waldo, and it's very easy to go find him, although it does take a bit of work to go find another Waldo. Although once you point it out, it's dead easy. I can just go say, hey, there's a Waldo, there's a Waldo. We know what we're looking at. We have consensus over what is in this space. You could imagine a hash tree, Merkle tree being made up of this. But ultimately, our ability to, be in consensus is limited by our ability to scan through the space and deal with this space. And that doesn't really scale too well. And we kind of run into problems when we try to apply standard database techniques. You ask any database engineer, and they're going to say, well, obviously, you get 10 different servers, you shard it, whatever. Some of the better ones will go complain to you about consensus. They do have all these same problems. But, in theory, it'd be very simple. Well, of course, if you are only seeing one of those shards of the chain, it's very difficult for you to go and determine whether or not double spend has happened. And the solution to that can easily be, well, why don't we go and assign different coins to different places? Why don't we go make the rule being that actually those are two different Waldos? And we can easily encode this in the definition of a coin. You can say, well, coin exists on this part of the chain. And I would argue that in a system like this, be it 4 chains or some crazy binary tree or something, I should be able to go prove to you that my coin is valid by showing to you that it was created, it existed from some point in time, maybe when it was spent, it was reassigned to another chain, but at each step, obviously I can go show you the data necessary to go prove this. And I call this a transaction history proof. And provided we have the property that we can get global consensus, or at least consensus among the people who care about these coins, for every part of that chain, then we have a valid proof. We don't need anyone else to validate it, we just need that consensus. Now, probably won't have time to talk about how we would get that consensus, but assume for a second we do. In that scenario, we also have another interesting property, which is if we have some kind of scheme for mining in this, where maybe some miners work on one part, some miners work on another part, if our protocol rules say that any block is valid, this can potentially scale, all right? Because if I go back a second, what's hard about this kind of system is, both those blocks are invalid due to data they didn't know. They needed to go trust other people in the system to do the right job. Whereas in a truly sharded system, everyone can work independently, and it's the clients. It's their responsibility to validate and make sure that the rules were followed. So there's your kind of intro to it. That's kind of what a transaction history proof would look like. Although there's a bit of a problem. I mean, if you wanted this to be convenient, we want to be able to take multiple coins in one transaction, combine them, and then spend them and split them, just like we do in Bitcoin right now. And if you look at the Bitcoin transaction graph, it has this property where you kind of get this quasi-exponential blow-up. And that, if you go pay me, and if I go backwards in history, pretty soon my coin is dependent upon every other coin in existence. And if I go back in time, like say a year, and invalidate one of those transactions, if the rules are that every transaction in history has to be valid, well, by definition, my coin's invalid. So if I'm going to go prove to you that, I need to give you all the data. That's not really practical. I mean, it is practical if you happen to have fiber internet to the home and maybe fiber to the cell phone, but we want to do better than that. So I think we can do an interesting trick, which is we can linearize that history. And what we're doing here is we're relaxing our rules a little. We're saying that rather than guaranteeing that inflation hasn't happened, we're guaranteeing probabilistically. Very simple way to go put it is you can imagine if you have a transaction with two inputs. If the rule is we go pick one of the inputs at random, and if the one input's valid, we go and prove it. If it's not valid, we say that the transaction's invalid. Well, let's go look at what the numbers work out. If we say X is our fake inputs, the value of the fake inputs, Y is our value of our real inputs, then we can go solve for what's our expected return on trying to fake something. Well, you can go do the arithmetic, but long story short is you end up with, by creating a fake input to a transaction, you're just as likely to destroy the real inputs. Because you can create these systems where you must commit in advance to certainly spending the coin. It has a certain probability of being picked, and if it picks the wrong way, if it picks a false input in your proof, you've destroyed real money. Now, the question, of course, then is, can you actually use, what do you use to go pick this? I mean, there's been some work done on modeling the blockchain as a random beacon, which is the idea that you have a publicly known, randomly picked number that no one can influence. You can go look up the papers on it. I believe, if I got my title correct, using the Bitcoin blockchain as a random beacon is the title by Joseph Benet or whatever. But, point is, I think there's reasonable approaches here that can go work. And I actually went off and did some simulations of this. And what's interesting about this is, well, what you're looking here is, imagine you go pick a random output in Bitcoin, and you go follow this back. You ask the question, how long does that proof end up being? Not the most readable thing in the world, but I'll tell you that second line up, 1,000, 2,000, 3,000, 4,000 transactions. Essentially, we're saying that nearly every transaction terminates in a coin being created out of thin air, a Coinbase transaction, in about 2,000 steps. And that number essentially comes out of the inflation rate of Bitcoin. Put another way, depending on how your model works out, this would be in terms of blocks. So this graph here, I'm saying, well, what block number did I end up at when I went backwards in history to create this proof? And interestingly, this graph's a little more linear, and I haven't quite figured out why yet. I'm going to have to do more research on the properties of this kind of transaction graph. But essentially with Bitcoin's inflation rate, which admittedly is kind of high, right now in actual real-world data, we're terminating at most under 300,000 blocks. Well, how much data do you need for a proof of publication system? The minimum, absolute minimum you would need to show that a transaction has been spent is probably on the order, or sorry, I should say, show that a transaction hasn't been spent, is probably on the order of something like revealing 128-bit key. So that's, say 16 bytes, maybe multiply with some overhead, depending on what exact mechanism you use. You can imagine this being, say, 100-byte proof per block to maybe a 1K proof per block. Well, what does that work out to be? Around 35 megs to 350 megs. This is beginning to be a practical system, where for me to go give you a coin, I'm giving you that many megabytes worth of data. Kind of sucks, but it's plausible that we could have a system where I transfer you even a gigabyte of data to go and give you a coin. And what's interesting about this is then if you can shard that underlying proof of publication layer, we actually have something that actually scales in a very big way. In that, I'm proving to you with data that nobody else in the world needs to see. It's very private in that most of the transaction graph is, well, can be completely discarded. So I think this is fairly promising. Of course, we do have one big caveat, which I think I need to mention, which is we found out that defining protocols is very tough. And in Bitcoin, because we have miners essentially testing to what the consensus is, it's very easy to determine when the consensus has failed. When one person is using a slightly different version of the protocol than another person. In these kind of systems, it isn't necessarily true you would notice that. And to give you an example, this actually out of the Ethereum yellow paper. It's not exactly the most readable protocol spec. It kind of looks a bit more like code. And yet what's interesting is this is probably the best effort I've ever seen of someone trying to specify a consensus-critical protocol in human text. And yet when the DAO bailout happened, well, the way they went and specified that extension to the protocol was a Medium post that links some GitHub gists. Because this is really too inconvenient to work with. And one of my goals with my work on the DEX language, there's a few other people like Russell O'Connor working on other variants along this line, is ultimately to make it easier to specify protocols. And that we could write in a language designed for this the definition of what, say, a valid transaction is, and then apply that mechanically to data. You would still have 10 different implementations for moving the data around, but we really got to agree on what's valid and what isn't. And before any of these kind of systems are really practical, especially for money, we have to go solve this problem. And I would not be surprised if, apologies to Blockstack, if they run into these kind of issues too. I mean, I know Counterparty and Mastercoin has also run into consensus issues across protocols. So this is going to be a tough thing to go solve, but there's your, I think, one of your big caveats on this. Thank you. Let's get questions.
Questions? First speech very clear for everybody. Oh, one.
We have a question.
Hi, I hope I just didn't, maybe I just didn't understand it, but it seemed like the miners are going to let anything into a block, and I wasn't sure, you mentioned transaction fees, but it seems like they have to prioritize the information that is included, or they just include one hash and they don't validate anything that they receive, or do they, to what extent do they even get any information at all and check it for anything?
Well, I mean, what's interesting about that question is, from the strict definition of the protocol, you don't actually need to define that. Now, in practice, I think that's a major engineering problem, particularly when we're talking about quite large transaction history proofs to pay anyone. But it'd be quite plausible to have a protocol which at the consensus layer says anything goes, yet in practice, you would go and give someone some kind of proof saying, well, you know, here's this transaction. It's not valid yet, but if you put it in a block, it will be valid and you'll be able to skim off the top of this output.
It seems, just to follow up this last thing, it just seems confusing to me. Maybe you don't have, so like right now we have this scarce resource of the block size, but it seems in your case it would be effectively unlimited because it wouldn't matter, and I'm just wondering if that is a correct understanding of, is it totally uncapped,
well,
and then there's no, the spam response is totally on the spender of the coin? That's
well,
the only
keep
thing
in mind, I didn't specify in this talk exactly what that proof of publication layer would look like. You know, I've done some work on that, for instance, my tree chains proposal, or tree change vision, if you will. Certainly isn't a full proposal yet. And you can easily imagine there being trade-offs ultimately between security against 51% attack and scalability. My suspicion is this is a fundamental trade-off. And ultimately, you know, what would be paying for fees is priority in that trade-off, in that particular type of system. Equally, I could imagine a simpler system where we say, you know, rather than having one chain, we're going to have 10, and we'll scale things 10 times bigger, but all the chains are basically equal and, you know, somewhat loosely coupled. And in that system, we essentially have a much bigger block size, but the miners have to go and process less data. You know, so I think there's a lot of implementation room there and a lot more room to explore.
Hi, maybe I didn't catch that. If you shard the blockchain into these, you had it in colored squares, how can I pay from one of these shards to another shard? Does that work, or are they pegged to each other, or?
That does work, and the reason why you can make that work is because when I go give you money, I'm proving to you the validity of it across different shards. So for example, if I start off in, you know, in a very simple system, your red shard, I'm proving to you that a coin was not spent for some part of history, and when it was spent, it was committed to a different place. And then for that next set of history, again, it was not spent, then it was validly spent and moved to another place. And even if anyone mining one particular shard doesn't have the full history, they're just proving that data was published and that data cannot be rewritten. I can still prove to you, by giving you the appropriate data for that particular coin, that all the rules were followed and it's a valid coin. You know, that's really the key difference there.
Thanks. Christopher?
So in some ways, you've got you're entangling the randomness over time, because you basically have a complex system in which everything is being entropically tangled by these proofs, such that you can't reproduce those without that time.
I'm not sure I'd describe it the way you did. I mean, I think the idea about reproduction is interesting because in these kind of systems, it appears that very little of the data actually needs to be public. As an example, if you have a transaction and the definition of a valid spend is I publish a valid signature for some hash, nobody else in the world actually needs to know what the signature means. In fact, you can conceive of a system where the actual signature is going into the publication medium, you know, the blockchain, if you will, are encrypted. And that's when I go prove to you I did not already spend that transaction output. I give you the decryption key. I tell you where to start looking and where to stop looking, and you scan through, test, decrypt all the data. Of course, it all returns garbage. And then finally, when the actual spend happens, you decrypt it, that's successful, you check the signature, you're done. But anyone else looking at that data from the publicly available chain, they don't know what it means. And I think this concept is very similar to Adam Back's committed transactions, but with the interesting thing that because it's client-side validated, the public doesn't ever need to have that data revealed. Whereas in Adam Back's transactions, it's a fungibility issue where, yes, it will eventually get revealed.
Two questions here. You mentioned DEX. Do you have more expanded reference for that? Because DEX is an ancient protocol. And
DEX is also a drug and probably many other things. You could probably buy it on the Silk Road. If you look at Christopher Allen here's work on the Web of Trust set of conferences, I think the best reference for DEX is at github.com/Web of Trust. Yeah, info, and it's under there by the name DEX. It's early days. I mean, this isn't a fully spec language. I can't point you to fully running source code, but that's why I said it's a progress report.
thanks. And second, in this system, would the shards be running the same protocol, and why do you believe they would have about equitable proof of work?
It entirely depends on how you implement it. I mean, chances are you would do it that way. If you read more about my tree chains proposal, that has a mechanism to split up the proof of work, but that's not really part of this talk yet. So
there.
So for the linearization, the randomized linearization of the proof, you need a public random source. And I guess the idea is to take that from a couple blocks in the future.
yeah, that's a tricky engineering question, because now if you look at that paper I mentioned, essentially what it's doing is finding how expensive it is to influence the result of that random beacon. And if you can, suppose you had full ability to influence it, essentially you can create money out of thin air, and that you can always go pick the one real input for a transaction that has many fake inputs. So what you really need to do is very tightly put bounds on how much mining power it would take, throwing away blocks that would otherwise contribute to the value, in relation to how much you can influence what the value is. I've done a bit of research on this. It looks like a simple way to understand this is to think in terms of the blocks being used as input to a random walk. Mm-hmm. And you can put bounds on how much you can go and move the final value. But again, that's one of these research questions.
Yeah, right. I mean, that was exactly my point, that, right, you can still influence the randomness, but at a certain cost.
Absolutely.
And if you just need to flip like one bit to make a invalid path invalid proof into a valid proof, then this might not,
Well, as an example,
possible,
with the
right?
random walk suggestion, it looks like you can make it, you have to have many blocks in a row to go and take a valid proof into an invalid proof. Similarly, you can actually imagine a system where this is the block reward. You institutionalize this fraud so that mining is what lets you go create coins out of thin air. And then the beauty of that, of course, means you're testing this whole thing from one end to the other.
The interesting thing is that I can test, right, like even before I spend my coin, it seems like I can test whether my proof will go through and whether it will go through with that randomness, and maybe depending on that, I spend it or I don't spend it, and maybe I can just send it to myself, and then in the next iteration I spend it because then the randomness is different. I feel like that's something to look at.
This kind of concept is similar to the Fiat-Shamir transform, where essentially you're bounding how much you can influence this simply by the fact that hash functions act as though they're pseudo-random number generators. So there's a fair bit of work to do on this, but I think it holds promise.
So last question, very, very quick, please.
All right. Is it an accurate oversimplification to state that there is a source of value and it's hash cache, and I'm going to present to you a proof that I possess a fraction of that hash cache, and you're going to validate that this is not double spent by using a proof of publication mechanism?
I'd agree with nearly everything you said, although I didn't actually mention what would be the creation of a coin. Chances are it would be a hash cache system, in that you are limiting the ultimate supply of it by making every block only worth so much. There's obvious ways to do this in tree chains as an example. But I mean, conceivably, you could use this for a centrally issued token even, where you have some initial issuance, and then from there on, it's proven in a decentralized system. So again, implementation decision.
Thank you, Peter.
Thank you.
15 minutes, the faster
Well, yeah,
coffee break of your
Giacomo,
life.
before
And before that, it is.
I want to talk about the workshops.
Yeah.
Okay.
So when you come back, you go directly.
Yeah. So we're gonna break for 15, 20 minutes, then we're gonna head to workshops. Okay, more like 15 at 4:45. So collaboration between the Bitcoin community and academia will be in here. Wallet implementation issues and discussion, it's the order on the program, will be in S1.3. Breaking the chain will be in S1.4. Block propagation S1.5, and getting into Bitcoin protocol development S1.6. Again, please appoint somebody to take notes. Also, people that took notes from yesterday, can you please email your notes if you have not to contact@scalalingbitcoin.org. We'll also have a leader that will report back, and we will return here at 5:45.
5:45 here.
All right, see you guys.
Hey. Okay, everybody, here is Elizabeth.
Hey guys, we're doing so well. We were almost on time. So let's get seated.
Okay, everyone, have a seat, have a seat.
So we can have the workshop report backs. So 3 minutes for each. Mikola, you need to get seated. Our epic journey in Milan is coming to an end. All right, let's get seated. Everybody coming back in the room. So each group is going to have a maximum of 3 minutes to report back. Come on in, guys. First, let's have collaboration between the Bitcoin community and academia.
That doesn't work. Okay. Okay. So hi. So we started at from in the first half of that workshop. So 6 or 7 universities make an introduction of that activities, and so we recognize that many universities already did joint research work with companies, and so we recognize the pitfall between the academia and the engineering communities. For example, engineering community, our business side focus on the short-term problem, but academia tend to think about the big picture of that problem. And so the current example of the collaboration is a private company sponsors an academic conference, and so some academic researchers provide the information of security evaluation of that technologies. We recognize that giving incentive to academia community is a fundamental issue. We conclude one great idea to enhance the communication between two. This is engineering Bitcoin core communities make BIR. BIR means that Bitcoin improvement request, and the BRR, this is a Bitcoin research request. This is a great idea, and so I think that it is so helpful to make research topic in academia community. And so we also discussed about the communication channel, and so at this time, we have mailing list and annual scaling Bitcoin workshop, but we additionally make a special GitHub or IRC channel and the open chat channel between the two communities. That's it.
Thank you, Matsuo. Next, we have wallet implementation discussion.
So wallet implementation issues and discussion. We touched a lot of topics, key management and hardware wallet integration, common protocol standards, definition of a signing protocol. We spoke about SPV, privacy issue, more validation, fraud proofs. We spoke about high-level libraries in general for wallet implementers, but also for things like joint market, Tumblebit, BitID, multi-sig support. We discussed coin selection, both in terms of privacy and efficiency, taint-based or different strategies, even exotic strategies like unlock time expiration. We discussed fee handling, problems with SPV wallets needing access to the mempool, miners having incentives to lie about fees if we decide to use fee information into Coinbase as a soft fork. We discussed making things more visible to users UI-wise, a bit like Uber search pricing, and using multiple providers as a solution for SPV wallets, similar to exchange prices. Smarter wallets remembering transaction history, how much they paid, and so on and so forth. Child pays for parent, transaction replacement, opt-in RBF. Open source software and deterministic builds in terms of wallets. In terms of key management, we discussed a lot how how to solve that in terms of better education, reminders to users as they use the wallet. Hey, have you backed up your mnemonics or your seed or that sort of thing? Maybe using external key recovery service with multi-sig. Tattoos. Biometric stuff. We discussed accessibility. I don't think any wallet provides accessibility to for blind people or deaf people, et cetera, et cetera. We discussed scripting support, Lightning support, payment channel support, interoperability across wallets so that you can reuse your seed across wallets, sweeping support, BIP70 and in general payment protocol extension for either shopping purposes, KYC purposes, AML purposes. Anonymous transaction push, and in general improving UI across wallets.
Okay, that's your 3 minutes. Thank you, Lawrence. Sounds like they did a lot on that workshop. Next up, breaking the chain.
So our section was Sybil attacked. There were actually two pretty distinct topics under the heading of breaking the chain. So I'm going to say something. I'm going to hand the mic to Peter Todd. On the topic of directly acyclic graphs instead of a chain, David talked about his algorithm Jute, which is a mechanism for ordering blocks within what I called previously a cohort during previous talks I've given on this. I think we all agree that in order to solve the 51% selfish mining problem and bring the security back to 51%, we need an inclusive policy. So we need to include all blocks, and that will solve the selfish mining problem. One point of contention that has been around for a while is how do you allocate transaction fees? David advocates for using a deep mempool and selecting from it in order to allocate transaction fees, which solves previous problems which had come up of fee sniping, where you try to rearrange the tree to take over a large transaction fee, or splitting transaction fees, which has other problems. Lastly, one point of future work which we have to deal with is David's talk basically revolves around all the blocks having the same difficulty. And that's what his algorithm does correctly. We still have to deal with the problem of how do we merge two histories with different difficulties. You're all probably Git users here. You want to do a Git merge. You can do that, but you have to have a merging rule. So we still have to figure that out.
And as you said, the other thing we talked about was essentially really going a little further into the context of my talk, how to go and actually implement this, particularly with my tree chains concept, which is a bit ironic because it's essentially taking multiple disparate trees and linking them together. The exact opposite of breaking the chain, taking trees and combining them. And to that effect, we really discussed in detail kind of what mining would look like there, how to pay transaction fees in a world where not everyone has the same data. We spent a lot of time talking about, what kind of strategies could you have to reduce load on the peer-to-peer network so that when I go pay a miner, I'm able to still pay them without necessarily having to give them like 5 gigs worth of stupid transaction history proofs. And that, I think, was a big topic there. And we also talked a bit about kind of how transactions will be structured, including the idea that you can go have a transaction that can be validated in part rather than only in whole, particularly with splitting transaction inputs and outputs. So inputs commit to Merkle sum trees of things to add to outputs. So you might have, say, one input actually send funds, in a sense, to an output that isn't yet complete without, say, 3 other inputs as well. And finally, I think we touched a little bit on just kind of like implementation issues, and like kind of what it would take to really kind of make this real. So thank you.
Next up, block propagation. You look lost, Matt. Are you okay?
Whatever, I guess. Oh yeah, calm down. I think we forgot to allocate someone to take notes, so we're just gonna ad-lib this, figure out, I guess, what we're talking about. We spent a bunch of time talking about like comparing extend and compact blocks. They're pretty similar, just some trade-offs between which direction the bandwidth is flowing and kind of the probability of which how many RTTs you do. We spent some time towards the end talking about mempool sync and about kind of ways to make these protocols more efficient, because they all rely on kind of having synchronized mempools between nodes to reduce bandwidth and hopefully somewhat latency. We talked a bit about like the Great Firewall and how shitty the internet is. The internet's a terrible, terrible place. It's awful. And we talked a bit about fiber and kind of ways to work around that. And
yeah.
Did you say? Yeah.
That's all, folks.
Yeah.
Yeah.
There's a lot of meat there, but yeah, it's mostly what we talked about.
Okay.
Last but certainly not least, getting into protocol development for Bitcoin.
Thank you. We had a really great discussion. There's a very wide diversity of different experiences. We had people who are brand new, people who have been contributing to core for many years, people who have implemented alternative implementations of Bitcoin, application developers, layer 2 developers, and also an Ethereum developer. So we had a great discussion. Bitcoin development's hard. It's really hard to get into, and there's a high barrier to entry. You've got to know, well, it seems like you've got to know a lot. So we talked about how we can lower that barrier, get people contributing in some way, getting started. So things we came up with, it's difficult to know what the process is for finding information if you haven't contributed much before. There's IRC, there's Stack Exchange, there's Slack, there are mailing lists. So it'd be nice if there was some pointer for new people to know where to look. We thought it'd be great if, as well as the hacker days after these conferences for the more experienced developers, there was something similar for newer developers, a place where they could ask questions of the more experienced guys and make their first contributions. I did a hacker residency last month. I know MIT has done a boot camp. That kind of thing's also great for people who are just getting into development for the first time. We talked about mentors. It's great to know someone who is a Bitcoin core developer to be able to ask questions. We talked about how it would be great if there was a developer advocate or a technical writer funded from the community somehow. There's documentation out there, but it's in lots of different places. Some of it's out of date. It would be good if there was someone who was looking at that. There's a lot of low-hanging fruit, so it's not actually impossible to get into Bitcoin development. There is something that anyone in this room can do, and a lot of developers can do, but people who are new to Bitcoin don't necessarily know that, so it would be great if there was some way of advertising that and marketing, an easy way to get into it. And finally, someone said it was good that there are multiple implementations, because not everyone knows C++. It's great that there are things like Bcoin, Bitcoin J, for people who prefer a higher level language. I think that was everything we covered. Thank you.
Thank you, John. One other point, since I was in that session, that I thought was really interesting was, so there are developer meetups for protocol development, and it could be good to have two tracks. One track for people that just have been developing, and then one that for people that want to mentor others and newcomers that want to start with the low-hanging fruit. So that was a point I liked as well. Okay, I'm going to hand it over to Giacomo. to close out this awesome 2 days we've had.
Okay, so, and with the chairman. Come. Anton. So, I would also like to invite on under the stage, you have seen Anton taking care of all the technical part, Ferdinando introducing the Scaling Bitcoin conference. We also want here on the stage Simona, that is actually the main responsible. We all have lived unforgettable moments, like a developer that we cannot call by name for Chapter Mouse rule, trying to demonstrate live 3 chains over there. Also the participation of a very famous actress as MC, and it was all beautiful, and I thank you all very much.
So, of course, we must thank all of you, attendees, speakers, people following the streaming session for such an engaging conversation and very good time together. Our MCs for being so precious, even when I get their last name wrong. And Anton was behind the scene, and so as all the presentations and the material and the transcript and the slides are available on the website, but more on that from Anton.
Right. Well, we covered a lot of very complex topics. Everything is available on the website. We've been updating the website, trying to turn it into a body of information so that developers who get interested in the related topics can come and have a single place where they can research, study, and get all this information in an efficient manner. So if anybody has any suggestions or input, please email us and give us your feedback. So we have a little gift from the organizing committee to the chair of this conference.
Oh, fantastic!
This is a wax seal, which is basically symbolically, it's this was used to seal the envelopes and packages in the past, and this is symbolically a well, it's a private key to the local hosting committee to be able to participate and join us in hosting the next event, for which we have a call for hosting on the website in the sponsorship section. If there's any companies who or organizations who would like to host an event in their geographical area for 2017, please contact us, fill out the form, and we will talk with you. So following that, there is quite a list. 1 second. That's hilarious. The phone just like...
In the meantime, I will ask also Pinder Wong to join us here. I mean,
So, special thanks to the local hosting committee, to Simona Macellari.
All the hard work has been done by
it would not have been possible without her. Gabriele Domenichini.
Jump. Like,
yeah. Stefano Capaccioli, this is a person, he's not here.
Not here.
He's an accountant who helped us deal with all the bureaucracy.
Helping me not to get in jail now, right now, after.
Giacomo, just marvelous. So with that, the local supporting organizations, the blockchain labs and SOB IT, you guys have been wonderful. It would not have been possible without you. It was really, really great. There's a lot of work goes into creating this, and it's the best team that we've worked with. So following that, some of our core organizers, Nelly Milanova, finance and logistics, all the way in the back. Pindar, without the without the guidance and expertise of Pindar, this would not have been possible. It's just marvelous to work with Pindar. Matt Corallo. Matt was the chair of the program committee, and we've been presented with a very difficult task of going through a huge amount of presentations, and it was very challenging, and that was just really amazing as well. Elizabeth Stark for managing managing the fellowship and handling all the subsidies, and it's been also a pleasure working with. Larry Salibra and Leonard Wizzi. Larry and Leonard are a part of the local hosting committee in Hong Kong, and they've handled all the technical and video feeds and such, and it was, again, this is an excellent team. Kang Si for happily helping us Kang has helped with Chinese relationships, translations. It was wonderful. I apologize if I missed anybody. This is a volunteer-run event, so a lot of you have contributed really a lot. So on that, I'll move on to the long list of sponsors. First, our platinum sponsor, Deloitte. The sponsor funds help cover the subsidies to different engineers and academics who focus on research and development, who otherwise would not be able to come. And Deloitte also sponsored the main reception yesterday at the Yard, which was really an amazing place. With that, our gold sponsors, Chain Code Labs, Blockstream, Conio, you'll get tired of clapping. BTCC, Bitcoin.com, Blockchain Labs, Block, Bitfury, Kraken, Entity Data, PricewaterhouseCoopers. Special thanks to academic supporting organizations. We were joined this year by the Stanford Computer Security Laboratory and École Polytechnique Fédérale de Lausanne, EPFL from Switzerland. And also special thanks to MIT DCI, who are one of our original underwriters who helped to make this event possible to begin with. So, go MIT. And the list of our bronze sponsors, without whom it also would not be possible. And they have also, a lot of people have contributed ideas and help. Green Address, Cyphex, Netkey, Digital Garage, Genesis Mining, F2 Pool, Slush Pool, Digital Currency Group, The Rock Trading, Yoke, Bitcoin Unlimited, Oracleize, Chainsmiths, Bitprim, Elevate, B3, which is a blockchain business board, a blockchain foundation, Eternity Wall, Ernst & Young, In Bitcoin, SpicePay, Azimuth, and List Group. Woo! So thank you, everybody. It's been a real pleasure, real honor working with you, and yeah, and see you in 2017.
Let's create Bitcoin. Bye. Already set.
Okay. Right. Close.